Title is SDN controller design for dynamic chaining of virtual network functions, presented by excuse me.
Chiara Condoli.
Sorry.
It's not that easy to pronounce. Thank you. Good evening, everybody. I'm Chiara Condoli from the University of Bologna. And we know that software-defined networking and network function virtualization are a good candidate for providing network for providing network programmability and flexibility. And in particular, NFV, which is about virtualizing network function traditionally implemented as vendor-dependent middle boxes, is gaining a lot of interest. This because middle boxes could be replaced by software appliances running on general purpose hardware provided by the cloud computing infrastructure. And we believe that this shift of paradigm will take place mainly at the edge of the network. In our vision, a future network operator infrastructure, the edge network will take the shape of a data center in which function will be provisioned. And this infrastructure must be flexible enough in order to allow what we call space chaining diversity, that is the capability of handling simultaneously active flows, and at the same time it must be also capable of handling what we call time chaining diversity, that is the capability of handling the possibility that at different time instance flows could be subject to different VNFs. So we decided to focus our attention in implementing the control plane that leverages the SDN approach. The goal of our work basically was to suggest a design methodology for implementing SDN control plane capable of dynamical steering traffic toward the required VNF, and at the same time it must be also capable of achieving fully adaptive service chaining. We considered a case study assuming to have a layer 2 edge network that we have implemented on the OpenStack platform. And now we can ask ourselves how I can design the SDN controller. So as a general approach to a service chain reconfiguration, we decided to adapt the abstraction provided by the Mealy machine, that is a finite state machine. And as a practical example, we considered the case of NFV principles applied in a multi-tenant scenario for dynamic enforcement of quality of services in order to satisfy the user service level agreement. So here we can see how the FSM looks like for the proposed example. And I want to point out that this is just an example because the FSN could also be different. And here is the formal definition. We have F defined as a traffic stream basically generated by the users. We have a finite set of state, a finite set of input, and this input could be generated by an event or by entities that interact with the SDN controller. We have a set of actions that at implementation time could be SDN technology dependent. And we also have a state transition function T that triggers state changes and the actions that must be taken during the state transition. So to have a look in more detail at the state definition, we have the init state, in which basically we install flow independent rules on the nodes in the network. We have the classification state, in which the flow F can be classified and analyzed. we have an enforcement state E, in which F is strictly subject to quality of service enforcement. We have the normal state, in which F is not strictly subject to this QS enforcement. And we have a state D, in which F is subject to some kind of policing actions. We also defined some other useful additional parameters, such as, for example, the set of switches, of ports, users, VNFs. And one of the most important things is defining the service chains of VNFs to which a certain flow F is subject when it is in a certain state S. We also define some other abstraction to get topology information, also based on the flow direction that can be inbound or outbound, and the capability of execute a certain command on a switch together with some optional parameters, the matching rules, and the actions that will be applied for all the matching flows. So here is the case study that we have considered, in which basically we have users that generates traffic, and this traffic will be forwarded to a deep packet inspector in order to be classified, and after the classification, it will be forwarded toward the required VNF. For example, the business user traffic will be forwarded to the one accelerator function. Therefore, we need to define the service chain, not only based on the users, that is not only based on the flows, but also on traffic network conditions. Okay, by adopting our approach to the case study that we have considered, here for brevity I will describe just the service chain definition for the business user, but of course the same can be done for other users. And I will describe the actions that will be taken on one of the switches in the topology, but of course the same can be done for all the switches in the topology. So, when the flow is in the init state or in the this state, no chain is applied. When the flow is in the classification state, the chain will be composed by the DPI, and the traffic will be also mirrored to the virtual router. When the flow will be in the enforcement state, the traffic will be forwarded to the one accelerator and to the virtual router. And during the normal state, the traffic will be forwarded to the virtual router that will leverage the legacy switching, basically. So, what are the actions that must be taken during the state transition? So, let's start from the beginning. When the SDN controller is in the initial state, basically we install flow-independent rules. And for a specific example, what we did is to install rules in order to avoid the ARP storm. Now let's see what happens when the controller moves from the init to the classification state, because a new flow arrives at the controller. First of all, we collect topology information about the users and the VNF involved in the chain. Then we define the open flow actions that will be taken on the matching flow. And as we can see here, we have actions that can depend on the underlying infrastructure. For example, the VLAN ID is used because in the OpenStack version that we have on our cluster, this is the mechanism used in order to perform the tenant isolation. Then we install the rules on the switch, and at the same time we also install rules that are capable of handling bidirectional flows. So what happens if after the classification the flow is found not compliant? Well, in this case, the controller move from the classification to this state, and for our example, what we do is to install rules that are capable of dropping the non-compliant traffic. On the other hand, if the traffic is found compliant, the controller will move from the classification to the enforcement state. But this because we decided to use a conservative approach. So in this case, the traffic will be first sent to the WAN accelerator and then to the virtual router. And in this case, the order in which the VNF are crossed matters. At the same time, we also install the rules so that we are capable of handling the bidirectional flows. So in this case, the inbound traffic will be processed in the reverse order. Just a few observations about the state transition. One of the advantages of this approach is that the steps that are taken during the other state transition that I have not reported here can be easily derived by properly modifying the steps that we have seen in these previous cases. For example, if the controller needs to move from the enforcement to the normal state because no network congestion is detected, what we do is to perform steps that are very similar to those we have seen in the transition from the init to the classification state. And if the controller needs to move back from the normal to the enforcement state, it can simply delete the rules that it has previously installed. So in this way, we are able to change the service chain basically based on the network condition. And another advantage is that the other steering actions can be easily replicated for the other users and, of course, for the other switches. So in order to prove the feasibility of our approach, we have developed a simple testbed on the OpenStack platform, and we used POX as a SDN controller, but we have an equivalent implementation with the real controller. And we have implemented the topology that we have seen in some slides before. And the users and the network function have been all deployed as a virtual machine on the OpenStack platform. In particular, we used an ADPI reader as a deep packet inspector, traffic squeezer as a WAN accelerator, and the Linux traffic control in order to shrink the bandwidth. While the destination and the network have been implemented outside the OpenStack cluster. Then we have tested throughput on relevant VNF ports, and we basically generated the UDP traffic flows by using the iPerf tool. So the following slides basically summarizes what we have seen so far. And if we look at the throughput measurement on the relevant ports, what we can see here are exactly the phases identified by the FSM. So results obtained show that we are capable of steering traffic not only based on network conditions, but also by legacy switching when an ad hoc traffic steering is not needed. We also decided to perform some measurements about state transition time during our experimentation. And we also decided to evaluate the round trip time and the latency introduced by the VNF, in this case for the flows that belongs to the residential user. And the mean values have been obtained by performing about 20 experiments. And basically we did not notice so many differences, but just because the VNFs were located on the same servers, but we expect different results if we distribute RVNF. So to conclude, we propose the design methodology for the SDN controller that is capable of steering traffic flows in a dynamic NFV environment. We considered the case of a quality of service enforcement in a multi-tenant cloud scenario, and we developed a proof of concept on the OpenStack platform to show the feasibility of our approach. And I was saying before, one of the advantages of this approach is that the FSM is able to capture the actions that must be taken on flows regardless the underlying infrastructure. Moreover, this approach is general enough so that it can be further extended in order to consider more complex cloud network scenario. We are now currently working on an orchestration approach in which distributed VNF are capable of providing feedbacks to some kind of service chaining orchestrator, so that the orchestrator is capable to talk at the same time at the cloud platform and at the SDN controller, so that it will be capable of react to traffic dynamics. So thanks for your attention. If there is any question, I will be happy to answer.
So any